Let's recap where we are in the class. We've started with kinematics and strain and stress under finite deformation. We derived the momentum equations, right? The conservation equations, so balance of mass, momentum, and energy, and the second law of thermodynamics. By the way, and then we covered constitutive model, starting with elasticity, generalized Hooke's law, and then plasticity and elasticity, right? So, right now you can actually solve with, once you learn how to implement those equations in a computer, you can solve any engineering problem across any discipline, except electrical engineering. Electrical engineering, you got to add Maxwell's equations. But all of engineering is just those 4 equations, I promise you. Every problem you've ever solved is just some special case of those 4 problems. Right? Or perhaps, some new constitutive model, like closure law, stress strain, conservation of mass. Sometimes we, use Darcy's law to simplify it. It's like a constitutive model for the velocity, essentially, right? Relating it to pressure. So next thing we're going to talk about is, where we're going is to talk about basically mixture theory, or how to, so everything we've done so far is just the mechanics of one thing, right? A solid or a fluid. I mean, the equations, they're all valid for solids or fluids. What would be different would be the constitutive models, right? So conservation of momentum, I think I showed this before, but we wrote it like dv dt, rho dv dt is the divergence of stress plus rho b, right? And this, if we're talking about a solid, then we have a generalized Hooke's law for our stress, right? Plug that in, then we have everything is if we have stress, C times the strain. Strain's a function of displacement. So then everything is in terms of displacements and their derivatives, right? That same equation also, I think I showed you this before, but what is dv dt, right? It's partial v partial t plus v grad v equals that thing, right? Well, that with a different constitutive model for stress, right? So, and we're talking about solids, we use generalized Hooke's law, right? Stress is a function of strain. If we're talking about a fluid, then we just say stress is a function of strain rate, which is like, it's really the, what's that?
Newton's law would be one.
Newton's law.
To relate stress
This is Newton's law, right? This is Newton's law. Conservation of momentum is, you're talking about F equals ma? Like that's F equals ma. But what we need to solve for a fluid is we need a different constitutive model, right? And typically we use something that's like related to the strain rate. So the stress is like some viscosity times partial V partial xij plus partial Vj partial xi, right? So that would be one constitutive model that if you plug that in and you put everything in terms of velocities, then you just get like the Euler or Stokes flow, right? When you have compressible density, then you have to add a pressure term, and then you get the Navier-Stokes equations, right? But it's the same momentum equation for a fluid or a solid. That's the point I'm trying to make, right? So now we need to know, like when we're talking about geomechanics, especially in our applications, we care about rocks with fluids in them, right? Reservoir rocks. And so we'll start by just considering a single fluid. It's actually the only thing we'll consider in this class, but the ideas that we're going to, the methodology that we're going to work through it would work for multi-phase fluids as well, okay? So we're just going to consider a solid and a single fluid, right? And so what we're going to do now is going to set out to basically, in the most rigorous way that I know how, derive those, and basically what I'm presenting is not just, I could just write down the final like polar elasticity equations, but what I want you to take from this is that the methodology that we're going to pursue here will work for any type of mixture. This is like a very generic mixture theory that I'm going to present, and ultimately will result in the Biot's equations or the polar elasticity equations, but you could use it to derive the mechanics of any type of mixture, okay? Multi-phase fluids, anything like that. All right. Now, we're going to start by, I'm just briefly going to mention the calculus of variations. So we're going to shift gears here completely for the rest of class today, but then we'll come back to mechanics on next Tuesday. So anybody know what the calculus of variations is? Or had a course in calculus of variations? Right? So the calculus of variations deals with problems like this, where you have an integral, say I. It's a definite integral, so it's bounded on both ends. And say you have a function that's really a functional, right? It's a function of functions. So the integrand of my integral is a function of time, a function of y, which is a function of time, and maybe even a function of y prime, which is a function of time, right? Y prime being dy dt, right? And what we want to know, and what the sort of whole subject of the calculus of variations is what is the minimum of that integral, okay? So in regular calculus, you learn like how to minimize a function, right? You take the derivative of it, set it equal to 0, take a derivative of it with respect to whatever you're trying to minimize it with respect to, and then set that equal to 0 and solve it, right? Very standard Calc 1 problem, right? But here, here we have a functional, right? So this is a function of functions, right? We have functions inside our integrand. And so the minimum of this is not a value. Like if you have a function and you're trying to find its minimum, it's a value. It's a number, right? Or a set of numbers if it's multidimensional, right? Here, the minimum of this is not a value, it's a function, right? And so the entirety of the calculus of variations deals with this. And I have a lecture just on the calculus of variations. And what I'm going to do is it's like less than 10 minutes, right? It's not long. I'm going to assign that as a homework, and I'm going to ask you a question from that lecture on the homework that I'm also going to assign today. All right. So, in order, I think I still owe you. We missed a class because of weather earlier in the year, right? I still owe you guys some additional material. So I'm going to assign that little 10-minute video as a homework, and then there'll be a question on the homework related to that video. And basically, that goes into more details about the process of, or more details in sort of the generic calculus of variations. But what we find out is that, to compute the minimum of this, what we do is we compute a variation of I. And we use a little del operator, okay? And in that lecture, it goes into more detail about what that del operator is. I'll write it down here as well. But, basically then you can show that we have to compute the variation of the functional, and then that gives us the minimum. So what's a variation, right? So basically, the idea is kind of like this, right? If you have 2 points, T1 and T2, and you're trying to minimize some function that connects T1 and T2, right? Or you're trying to understand what the minimum function is between T1 and T2. Who knows what it will be, right? But basically, in the way you do that is you take these variations, and what these variations are just arbitrary. They're truly arbitrary variations, right? So they're just other paths, other potential paths that you could take You can think of them like a family of other potential paths between T1 and T2. And then when you basically solve for the minimum of them, then it will give you the actual path between T1 and T2. Yeah.
For my calculus 101, integral is supposed to define an area under the curve, like
Yep.
T1 to T2. When you say you're trying to find a minimum, are you saying like I want to find the minimum area possible? Because that would be like dead down to the ground.
Yeah,
Zero.
it's you're trying to find the function that minimizes this integral, right?
So in that case, it should be like zero, right? Like it just goes down.
Well, it depends on what this functional is, right? We can't. The classic problem is actually, and I'm trying to avoid talking about it because it's in that lecture.
Okay.
But the classic problem is actually called the brachistochrome problem, and it's what is if I have a ball of mass m located at T1 and I let it go, and that ball is set to travel along a path to T2. What is under gravity? That's important. Under gravity, what is the path that will get you the fastest would get the ball the fastest from T1 to T2? You would think it would be a straight line. You'd think it would be a straight line because the shortest distance between right? But if you take a straight line, and in the lecture I'm going to assign, I have like a computer animation. I solved this problem. I have a computer simulation of the problem, and then I have a link to a YouTube video where there's actually shows an experiment of this exact problem. And what the actual path is an arc called a cycloid, and it's because it's under the force of gravity, right? So you have gravity, and so initially, for it to have you can pick up more speed if it has a steeper slope, right? If it has a steeper slope, you can pick up more speed and then curve. And so there's actually an experiment where somebody built that, where they have like a cycloid and then they have a straight one. They have two balls and they release them at the same time, and you see that the cycloid wins the race, right? So yeah, I'm trying to avoid talking about it because I already have a lecture on it, and we just want to use it today to solve a couple of problems or like demonstrate a couple of problems. Okay, so let me first then show you what the variation operator is. Okay, so the variation operator all right, so if we have a variable, field variable q function, and we want to compute its variation, right? That's the lingo, right? So imagine if we stuck q there, we want to know what del q is, like what the variation of q is. Then what we do is we create a new function q star, where q star is q plus a small value epsilon times del q. And then you plug that into there, and then compute this integral and evaluate it at epsilon equal to 0, and that's going to give you that. Most of the time, and I'm going to show you an example, most of the time it works almost just like a differential operator holding time fixed, okay? So these variations are done in fixed time, okay? So most of the time it works just like that, like and it's actually interchangeable with the differential operator. So if you have like the variation of a derivative, that's the same thing as the derivative of a variation. So it's very much like just a differential operator with time fixed, okay? So let's look at an example. Let's say I have an example where I want to compute the variation of a function t. That's a function of the velocity vector and time, all right? So what I'm going to do then, and I guess it's also necessary to, well, yeah, what I'll do is I'm going to say partial E T V plus epsilon del V evaluated at 0. And then what I'm going to do is I'm just going to create a new variable U that is equal to V plus epsilon del V. Right, so basically this is just for convenience, because I'm going to compute a chain rule in a second. And so I want to basically take what's in the integrand there and just assign it to U. Okay? So with that, then, using the chain rule, I would have partial T, partial U, partial T, partial U, partial U, partial epsilon, evaluated at epsilon equal to 0. All right? Well, partial U, partial epsilon is equal to del V, right? Just taking the partial derivative of this expression, right, with respect to epsilon, it's just del V, right? So then, also U evaluated at epsilon equal to 0 is just V. Right? U evaluated at epsilon equals to 0 is V. So this first thing becomes partial T partial U. I'm sorry, partial T partial V, because those are equal. Partial T partial V del V, right? So then the final result, partial T partial V del V. All right, so that's just an example of using the variational operator and that's no different than if I, basically asked you to compute like an increment D held fixed in time, right? This is, you would get, if I said, what is dt, then you would say partial T partial V dV, right? So most of the time, this is just interchangeable with the differential operator. We will see an example when we start deriving the poor elasticity or mixture theory equations. So one case where you have to do something special, and that's why it's useful to define this more formally as this kind of partial epsilon thing. That will be useful in the next week. Okay. So let's see then. Okay.